Hi, everyone. My name is Amy Sullivan, and I'm the chair of the AAAR Endowment Committee. It's my pleasure to welcome you to our fourth in our monthly series of AS&T paper lectures. This is a new initiative for AAAR, supported by the Freelander Memorial Fund. With this initiative, we hope to be able to highlight all of the amazing research happening in our community, to be able to tie our journal to other activities, and also give us an opportunity to all come together outside of the conference. So each month, the editors of AS&T pick a high impact journal article to be presented by its author. These lectures are being recorded, and you can access them through AAAR's new YouTube, and there's a link on AAAR's webpage under the events tab. In addition, each of our lectures is being hosted by one of AAAR's student chapters. And in addition, for many of the lectures, the student chapters have organized a journal club that meets the week before to discuss the paper. So students look out for an email about that. I want to thank everyone who's helped in making all of this possible, and for all of you for joining us today. And so now I'll turn it over to the University of Florida student chapter to get us started. Thanks.
Thank you, Amy, for briefing the session. Good afternoon, everyone. I'm Shripriya, a PhD student in the Aerosol and Particulate Research Lab at UF. So it's an honor to introduce the speaker of today's lecture, Dr. Anita Avery. She's a senior scientist at Aerodyne Research. She did her undergraduate in environmental chemistry at the University of California, San Diego in 2010, and she earned her PhD in environmental engineering in 2017 from Drexel University, where she focused on the relationship between indoor and outdoor air quality. Her postdoc led her to Aerodyne in 2018, where she now works on development of several instruments. Soot Particle-Aerosol mass spectrometer is one such device she has been working on, which is used to measure both refractory and non-refractory aerosol components. Dr. Anita will share more on particle deposition using the dual-vaporizer configuration of the Soot Particle-Aerosol mass spectrometer for the next 45 minutes. And after our talk, we will have a Q&A session for about 15 minutes. So please put down your questions on the chat, or you can unmute yourself after the lecture. So with that, over to you, Dr. Anita, it's all yours.
Well, thank you, and thank you for that introduction. It's an honor to be here, and it's an honor to be talking about this work and working with AAAR. AAAR has been my professional home for my entire career. It's my first conference, my first talk, and I think Amy Sullivan was the first person I ever got the courage to ask a question to at a conference. So I'm really happy to be here. As we mentioned, I'm going to talk about the SP-AMS. But I really would like to, I know everyone says, please ask questions, but I really do mean it. And if we don't get to your questions today, I put my email address at the bottom, or you can find me on Twitter. Please do ask questions. That's why I'm here. So I'd also like to start off thanking my co-authors, Leah, Ed, Wade, and Tim. This is all possible because all of these people and a lot of others have been working on AMSs for longer than I have. I wouldn't be here without the work of my co-authors, both now and in the last 20 years. So because this is going to get into some really nitty-gritty details of how the SP-AMS works, I'm going to start way at the very beginning on how the AMS works in general. So we say that the AMS measures size-resolved chemical composition, organics, nitrate, sulfate, ammonium, and chloride. And this is a figure from a 2007 paper. It's similar to the Jimenez 2009 science paper, all the places that the AMS has gone and the similarities and differences in chemical composition based on rural versus urban, and huge range of concentrations and some pretty significant differences in fraction of each of these components. And this is all based on John Jane's first AMS paper with the quadrupole AMS in 2000, then the time-of-flight mass spectrometer in 2005, and what we call high-res mass spectrometer in 2006. In 2007, Nagratna wrote a extensive review paper, which would be impossible to do today. So this is 14 years old. And trying to summarize what has happened with AMS instruments throughout the world is really not possible. But the idea here is that we can look at this composition measurements throughout the entire world, and we can apply the same kind of instrumentation. So what this graph is showing is these non-refractory components, the organic nitrates, sulfate, ammonium chloride. But what's missing here is things that don't vaporize at 600 degrees Celsius. So for us, that's usually things like certain sea salts, dust, and for our purposes here, metals. So that's a fraction of this pie that we're missing, and especially in urban regions more close to sources of black carbon, that can be a major fraction that we can't see with the normal AMS. So in 2012, Tim Monash's paper, also published in ASNT, introduced the SP-AMS. So everything about the AMS that I'm showing in this figure is the same between a standard AMS and an SP-AMS, except for this laser that is coming in and out of the screen for you, in and out of the page. I'm going to briefly talk about all of these components and how the mechanism works to bring the aerosols in and detect them. So we have the inlet brings in the particles. They go through an aerodynamic lens to TOR. This focuses in the particles. We lose some of the small particles in this process. And then it goes through several differentially pumped chambers. These are all dropping the pressure of until we get down to 10 to the -6 or so TOR at the detector. So the main idea here is that we're trying to keep the particles in a beam while dropping the pressure. So the particles come in, they go past the chopper, and the chopper can either be an open position where it's not in the particle beam, a closed position where it is blocking the particle beam so we can detect the instrument background, or it has the slit in it about 2% of the time. It's spinning, and it's what that does is the particles are blocked 98% of the time, and then it sends kind of these packets of 2% at a time that go from the chopper to the detector. So you can kind of see that here, that it's chopping these, and then we can measure based on the time of flight from the chopper to the detector. We can measure the particle size distribution based on that time. So the particles, we're not going to talk too much about PTOF, but just for functionality here, that either the chopper is usually open or closed. And so the particles that make it to the vaporizer, so this is the ion chamber here in gray. And what we see is that the laser is in front of the tungsten vaporizer, which is in green, and it's surrounded by the ion chamber. There's a slit in the bottom. Vaporized particles will be ionized by the filament below, and then the vaporized ions will go up into the detector and be detected by, in this case, a HR-TOF, time of flight mass spectrometer. And so the idea here is that regardless of which vaporizer you use, you're still using the same mass spectrometer. We've more recently attached a better mass resolution mass spectrometer called a long time of flight mass spectrometer, or an LTOF. But the idea is the same, that regardless of the detector here, we have the same mechanism in the ion chamber region. So what does the laser actually do? So this is again from Tim's 2012 paper, and the laser itself is a 1064 nanometer neodymium YAG laser, and it is used because black carbon and most metals absorb at that wavelength, and in that absorption it heats up and evaporates, and we can detect the vapors and detect the ions that result. This is the same laser as the SP2 made by DMT. And what you can see in this figure here is that the benefit of having mass spectrometry here is that if you have some kind of black carbon core with a green for organics coating, and it comes into the laser, the black carbon core will see the laser heat up, and the core will heat up enough that the coating starts evaporating first, and then until there's no more coating, and then the core will evaporate by the time it gets through the laser. So in a SP2, you can see that you get the scattering and incandescent signals that are different based on the coating to core ratio here. And then for our purposes, we care that both the organic and the black carbon components are ionized and can be measured with the mass spectrometer. So we have the green organics and the black carbon. And what we really like about this is that we have the same detector regardless of which vaporizer gets used. So for the coating on a black carbon core, as Tim and some others like to say, that the laser is not the vaporizer, the absorbing particles are the vaporizers. So that's what's heating up. That is what is causing the heat for the coating to be able to evaporate. Okay, so I promised some details on the ion chamber region. I'm going to spend most of my time talking about this region. So I've shown it both as the figure on the left, and then I really like to see pictures of what these look like in real life. So I've shown a picture from the same perspective on the right. So first we have the particle beam coming in from the left, and we see that there's this hole in the, this is the ion chamber here. On the left, it's these gray lines on the top and bottom. On the right here, it's this rectangle. If you look from the particle beam perspective, it's actually a hexagon. But the hole here is for the laser to go through. So I'm going to try to keep my laser pointer here in the same position as maybe the laser itself would be. But the laser here, so as the particles come through, they interact with the laser vaporizer first, and then it hits the tungsten vaporizer on the right. So it's an inverted cone. So in the schematic, you can see that with the green shape, it looks like a wedge. But for our purposes, we see it kind of as a vertical line coming into the ion chamber. So we want the vaporizer to be coming into the hole in the ion chamber so that there's good overlap between where the particles are vaporized regardless of which vaporizer is used. So you can, so that they'll both be ionized and extracted the same. So the filament comes at the bottom. So this is a wire that's about, I think just under 1 centimeter in width. And so that is ionizing the vapors from either vaporizer, and then the ions are coming out of the top to go to the mass spectrometer. So I'm going to talk about the physical characteristics of all of these components. First of all, is that this hole in the ion chamber is about 5 millimeters in diameter. The tungsten vaporizer is about 4 millimeters in diameter. In this space, it's a vertical distance. And then the laser vaporizer is about 1 millimeter in diameter. And so this laser vaporizer is much smaller than the tungsten vaporizer. Finally, the ionizing filament is about 8,000 degrees Kelvin. So that's really, really hot, and it's about a paper's width distance between it and the ion chamber wall. So that's going to be contributing most of the heat to the ion chamber. In this instrument, I don't have it pointed out in the figure here, but we added some thermocouples to the ion chamber. So you can see this right here on the left, this installation for the actual thermocouples. And the ion chamber is also heated by the tungsten vaporizer, which is set at 600 degrees Celsius. So the different modes of operation for the SP-AMS, there's 3 different ways that it can be run. One is if you turn the laser off, you just have a standard AMS. And so you set your tungsten vaporizer to 600 degrees Celsius. You get your non-refractory material, your organics, nitrates, sulfate, ammonium chloride. And you have just a regular AMS, and it behaves in the same as a standard instrument. You can also operate this instrument as laser only. So if you remove the tungsten vaporizer and just leave in the laser vaporizer and keep it on all the time, you can see just the absorbing particles in their coating. So you'll see anything that absorbs at 1064 nanometers and everything that's heated up from that absorption. So what people also like to do is run in this what we call dual vaporizer mode. So if you leave the tungsten vaporizer in, and theoretically, this would be the best of both worlds. This would be all at once. And you would, when you have the laser off, you just have the normal AMS and you get the standard NRPM. And when you have the laser on, you get the refractory species and NRPM. But we'll note that these are not the same terms, right? So this non-refractory PM also includes both things that are vaporized by the tungsten vaporizer that we see in the laser off, but also any kind of coating or other material associated with the RBC. So these two NRPMs are not the same. And this difference between these two is going to be the source of a lot of questions that have come up over the last 9 years. For the record, we think that the laser only mode is often the best way to go. But this dual vaporizer can be really useful when you want to be able to get as much information as possible in a short amount of time. So what happens when you run in the dual vaporizer mode? This is some example data from the Clearflow campaign in the UK outside of London in 2012. Leah Williams took this data. And what we can see is that the laser on concentrations in the vertical axis and the laser off concentrations in the horizontal axis, we see that the slope is greater than 1 for all of the standard species. And we see that there's some differences. We expect something like the organics over here to have a higher laser on to laser off ratio based on more coating. Organics are more likely to be coated on the black carbon than the other species. And in this situation, there were really aged aerosols that are probably really, really well internally mixed. And so the rest of these are a little less surprising. But in general, it's a little uncommon to see black carbon quite as internally mixed with something like ammonium nitrate. And we see this all over. So this is the one data from 2012, but we've seen this a lot of places before, even environments that have more fresh black carbon emissions and little internal mixing. Alex Lee in 2015 did a bunch of work trying to look at single particle measurements to get at this question of why we see higher laser on than laser off. And he did some work with single particle measurements there. So why is this happening? Is it only the internal mixture? Is it only, are these purely just the difference between the slope line to the 1-to-1 line? Is that all because of species that are associated with black carbon or not? So since we're getting into the nitty-gritty details of how we quantify all of these compounds in an SP-AMS, I'm going to start off with how we quantify anything in an AMS. So in order to get the mass concentration in micrograms per cubic meter, I put the equation up here on top and the units right below it. So for that mass concentration, where does that number come from? So the first item here is the summed ion rate, which is just the literal signal that comes out of the instrument, so the ions per second. We subtract out the closed signal, the chopper closed from the chopper open, and to remove instrument background. And this is just the raw detected signal. So, without any better quantification, this would be a qualitative number that says there's a little more this time than at this other times. But this is just what we get out of the instrument. We also need the flow rate to know what volume of air is being brought in and how quickly. So that's just the flow rate Q. And then we have this mass-based ionization efficiency of ammonium nitrate, MIE-NO3. And this is just our primary calibrant. So we can use 300 nanometer ammonium nitrate. And this will give you a measurement of the instrument sensitivity, any difference in voltages or extraction frequency or other instrument parameters that we have over the lifetime of an instrument. We can track that and calibrate how the instrument is operating at any time with this ammonium nitrate calibration. And then we get into these other two parameters. So the relative ionization efficiency, RIE, this is a single number that we relate the ionization efficiency of any compound like all organics or sulfate to that of nitrate. So when we go out and calibrate, we only have to calibrate with the one compound, or with an SP-AMS, we measure with black carbon as well. But we only really have to measure the nitrate. And then we know the relative ionization efficiency of other compounds with respect to nitrate. There's been a lot of studies, even one recently, that came out looking at the RIE of compounds emitted from indoor aerosols from cooking. And in general, we assume that both of these, the RIE is the same for both vaporizers since the ionizer is the same. And that's an assumption that we've made to date. And there could be some deviations from that, but that's the primary assumption. The second is the collection efficiency. So what proportion of the particles that enter the instrument get to the ionizer? So there's a few loss terms that I'll be talking about. And so when we think about both of these, I'm just highlighting here that both of these are dimensionless numbers. And a lot of times when people are describing one or describing another, they kind of conflate the two, because if we don't know one of them really well, it can appear to be the other one or vice versa. So if you're trying to understand the collection efficiency, you have to know the RIE and vice versa. So these two terms are really important for any time you're using AMS, but we sometimes conflate the two. So just looking at the collection efficiencies, first of all, this is the equation. So the equation is the product of three different loss terms. The first is losses in the lens. I mentioned that we mostly lose some small particles. So for a mass-based instrument like the AMS, that's less of an issue. There's been lots of studies looking at the losses of the losses of the particles, the size range of each AMS. There's been a lot of studies about that. The second term is this particle shape, losses due to non-sphericity of the particles. So we know that non-spherical particles, that as they leave the lens, they tend to spread out. I mentioned before that the tungsten vaporizer is about 4 millimeters tall, and the laser vaporizer is about 1 millimeter. And so when we think about this non-sphericity parameter, the compounds, particles that are going to absorb things like black carbon are less likely to be spherical. They're more likely to spread out, and they're trying to hit a smaller target. So they're trying to hit a 1 millimeter target in the middle of the ionization chamber instead of a 4 millimeter target. So that's much more of an issue for the laser vaporizer than the tungsten vaporizer. And then finally, this bounce term. This is primarily for the tungsten vaporizer, things that literally bounce. The particles come in on the left, they hit the tungsten vaporizer and bounce off and don't fully vaporize. So there's been a lot of work looking at this. For both field and lab studies, we find that it's composition and RH dependent. And it even got to the point that there was a development of the capture vaporizer, which is also used in ACSMs to combat this issue. So a redesign of the vaporizer to combat this issue. In the laser vaporizer, this can also manifest as partial vaporization. So if a particle kind of skims the outside range of the laser, it might partially, but not entirely vaporize. So the last thing I'm going to mention is that just to note here that the collection efficiency for ammonium nitrate, 300 nanometer ammonium nitrate is 1. So that's why we use it for the ionization efficiency that we talked about the last time. It's because we know that it's 300 nanometers is a size that is not lost in the lens, that it's really, really spherical and it hits the vaporizer very efficiently. And it doesn't bounce at all. It's so volatile that there's virtually no bounce for ammonium nitrate. But what about the other particles? So what's the fate of these bounce particles? So I've shown in this little schematic here that the tungsten vaporizer is inside the ion chamber. So when particles bounce, and we know this happens with up to 50% frequency, what happens to these particles when they bounce off? Where do they go? So when we go back to our modes of operation, where do these CEs come into play? So for the tungsten only, the shape factor isn't really an issue, and the primary driver of the collection efficiency is in this bounce term. For the laser only, There's no literal bounce, but you can get the partial vaporization. But that's generally a small effect compared to the shape factor. And then with the dual vaporizer mode, again, you're trying to do all these things at once. These NRPM terms in these two equations are not equivalent. And you have to deal with that this shape term and the bounce term are both well under 1. And so calculating the CE for a dual vaporizer mode becomes really difficult. And if you think, especially for ambient measurements, if you have some kind of fractal black carbon coming to your instrument with different amounts of coating, you're going to have both of these terms, or maybe even all 3 of these terms changing at once. And so this becomes a really difficult thing to tackle for the dual vaporizer mode. Okay, so I mentioned what happens when the particles bounce. What happens when we hit tungsten vaporizer and it lands on the ion chamber? Will they vaporize off the ion chamber? So this is a figure from the paper that I show, this isn't how we operate normally, but if you just turn on the filament, how much heat does that provide to the internal components? Where does that get you? So for the ion chamber temperature, it heats up to about 225 or so degrees, and then you turn the laser on, and that provides some heat load to the ion chamber, maybe 40 or 50 degrees in this example. But your vaporizer, even when your vaporizer is turned off with no heat load applied, it's still above 150 degrees. So that's why if you're going to run in laser only mode, you want to remove the tungsten vaporizer because there's lots of compounds that would still vaporize at these temperatures, even though you've turned the vaporizer off. For normal configuration, for normal sampling, you have the tungsten vaporizer set to 600 degrees, and the ion chamber, as a result, is heated up even more, and about 280 degrees is the laser off temperature. And so I'm going to talk a lot about this difference between the laser on and laser off temperatures. So here it's about 50 degrees in this example, but it can be much larger. So what we want to know is if the particles bounce off of the tungsten vaporizer and land on the ion chamber, what is the detection efficiency if they land at this temperature or at this temperature, or in another situation at a much higher temperature if it's heated even more by the laser vaporizer. So why does this matter? This is a figure from Wen Zhu's paper in 2017, where he was changing the tungsten vaporizer temperature down from 600 degrees to show the detection efficiency of various compounds at these lower temperatures. And so what we see is I've shown the about 280 degrees Celsius ion chamber temperature at the low end of the box, and then kind of the maximum level that we see that I'll show later at this difference in ion chamber temperature here is about 90 degrees, so about 270 degrees, 280 degrees Celsius. And what we see is between 280 and 270 degrees Celsius, the detection efficiency of sulfate and the detection efficiency of organics changes by a factor of 2. And so for sulfate at 280 degrees, it's detected about 30% efficiency, and at the higher, maybe a laser on ion chamber temperature, you get up to maybe 60% efficiency. For organics, it's between about half and full detection for alpha pinene ozonolysis SOA. So we think that this this temperature difference here for the ion chamber can have a pretty significant effect on the detection of especially these less volatile components that we see in the AMS. So going back to the figure from the ambient data from the UK, let's think about what could be causing this laser on to be higher than laser off. So this first explanation is that the heat load on the ion chamber changes with laser state. Non-refractory species bounce. Edmund Cross in 2007 showed that things that bounce off of the tungsten vaporizer are vaporized. And he did this using the light scattering module. So when the laser is on, it's hotter. and therefore the non-refractory species are more likely to vaporize. And this hypothesis doesn't require any knowledge of internal mixture versus external mixture, and it's a really controllable parameter that we can explore here. It could also be because of these CE differences that I've talked about, so different levels of coating on the black carbon could be detected with different efficiency based on whether reaches the laser vaporizer or could be partially vaporized on the tungsten, so that'd be a difference in collection efficiency, or be RIA differences that are assumption that they're the same based on the two different vaporizers. We know that when that the fragmentation pattern is different for particles that are vaporized with the laser than particles that are vaporized by the tungsten vaporizer because the temperature is lower. We know that there are some vaporization differences, and so they could potentially lead to some RIE differences. That's something else that could be causing this effect. We're going to focus here on this section. We're going to look at this heat load. We're going to add some baffles throughout the course of the laser to try to reduce this heat load and focus just in on this one parameter that we can control relatively easily. So in order to do this, we added baffles in 3 different locations. So I've confused it a little bit that I have 2 different perspectives here, but so this primary perspective in the schematic is from the perspective of the particle beam, and then I've shown the previous image of the ion chamber from the perspective of the laser camera. But the 3 different baffles we put in were named for where we put them. So in the right on top of the crystal that's used for the laser, the neodymium YAG crystal itself, there's a spool of thread type piece that we could add in a restriction. And so it's right on the crystal of the laser, so we called it the crystal baffle. And then internal on the chamber, there's a cylinder that holds the pump that's below this chamber in the vaporization region. And so that cylinder has a hole in it for the laser to go through, so we were able to put a baffle there. So we called that the cylinder baffle. Very unique in our naming. And the stack baffle here, so we were able to attach a baffle to this lens stack. So it's kind of cut off in the picture, but the lens stack up above. And so we can make an attachment that just comes off into the page here, but is directly attached to the lens stack. So we called it the stack baffle. And so we also added this thermocouple to the ion chamber. And so we're going to measure the temperature difference between the laser on and laser off on the ion chamber and on the tungsten vaporizer. And we're going to analyze these baffles. So we had a 2 millimeter, 3 millimeter, or 4 millimeter baffle in all these positions. We also did some mixtures. And we're going to judge all of the baffles based on 2 criteria. One is how well it restricts light. So how well it restricts the excess light, excess heat for the on the surrounding elements. The other is a positional restriction. So if I use my laser pointer here as like the laser itself, the particle beam is coming in from the left, and so we need to be horizontally aligned so that the vertically aligned so that we're intersecting the particle beam. If we're too high or too low, we won't be intersecting the particle beam. But there's really nothing to restrict the laser in its current form between going all the way to the right or all the way to the left. So we want to positionally restrict that so we're right in the middle of that ion chamber, so we have the best detection regardless of which laser we're using. Okay, so we use these 2 criteria to judge the effectiveness of each baffle. So the first one is the positional restriction. So this is a schematic that's to scale. So this is the laser source on the left and the ion chamber face on the right. So this is from the particle beam perspective. The tungsten vaporizer is somewhere right here and much larger, as I mentioned. So the idea here is that if you consider the laser as a point source from its source, And then kind of if you could angle the laser all the way up or all the way down or all the way to any side, you would hit the ion chamber face that's denoted by this green line. So this is the maximum angle that you could take, and you would exactly hit the edge of the ion chamber face, and this is in axial distance, so or bottom. So the baffle is smaller than, the places where the baffle is smaller than the projection of the diameter is smaller than the green line is where there will be a positional restriction on the baffle. So I put the, again, to scale the 3, 4, or 2 millimeter baffles in each position. So for the crystal baffle, none of the 3 baffles are smaller than this green spot, green line in this spot. So none of them at this point restrict baffle position. The baffle, only the 2 and 3 millimeter provide positional restriction at this point, but the 4 millimeter does not. And at the stack baffle face, this is that they would all 3 provide some positional restriction. So if this is a term we want to optimize, we can choose probably one of these last 2 baffles, and the smaller the better, in order to get this maximum benefit. So for the light restriction, this is a fairly basic figure, but just kind of to give a perspective, because we're really bad at radiuses. This is the 2 millimeter, 3 millimeter, 4 millimeter diameter as lines, as we showed before. And this is the laser diameter at the ion chamber face. It's spread out a little from the source to the ion chamber. And so you can see that this ratio is just this baffle diameter to the laser beam diameter. So pretty much no matter where you put it across the laser space from left to right from the previous figure, that's not going to change very much. So it's going to be primarily based on which baffle we used, what size baffle we used. So I've switched here a little bit. The vaporizer is now on the left. I did this because when you look at the camera perspective, if you're looking on the instrument, you're moving the laser around and you're looking at it with the laser camera, this is the perspective you see, is that the tungsten vaporizer is on your left. So the way this looks is I've drawn in the ion chamber diameter in black here. And so this is what you see, or what you don't see when you're looking at the camera image, but what you would see if you could see the ion chamber diameter. And it's bigger than the area of the grid that you can see with the camera. And without a baffle in these black points, there's really no restriction on where those points can end up, right? So again, in order to be intersecting with the particle beam, which in this case is coming from the right, you can't be too high or too low, or else you'll not be in line with the particle beam. But there's really no restriction on left to right in these positions. But what the cylinder baffle does is here on the in the blue lines, this 2 millimeter baffle is essentially restricting these to really the center of the screen, and really the center of ion chamber. And what you can see is that even moving around intentionally moving around the laser position significantly with these blue X's, the positional restriction really does keep it to within this circle denoted by the blue. So how effective are these baffles in reducing the laser on minus laser off temperature of the tungsten vaporizer? So for the tungsten vaporizer, it's only on one side of the instrument, so it's on this left side. So what we can see is that when the lasers to the right, or in the kind of more centered positions, see a laser on minus laser off temperature difference of less than 10 degrees, which we're generally happy with. We're not going to see much of a effect of that based on the ion chamber, based on the tungsten vaporizer temperature. We're not too worried about that. But if you don't have a baffle in and you move it too far to the left, you're going to start seeing these big differences in temperature change between laser on and laser off. So this over here that we hit 40 degrees Celsius difference between laser on and laser off, we're going to start seeing a difference in detection potentially. So with this different restrictions with this blue baffle, even when you do shove it all the way as far left as you can, we're still able to keep this temperature difference below 10 degrees Celsius and usually even better than that, usually closer to 5 degrees difference. I'll note that here that the scale here is correct for what we did, but because you can remove the tungsten vaporizer, that when you put it back in, it might not be in the exact same spot every time. So the positional restriction will also help if you accidentally have put your vaporizer in a little bit farther than you want to, so it will help with that issue as well. So for the ion chamber temperature, so again, the laser on minus laser off temperature of the ion chamber, we see that we see that there's a lot of scatter here. That is because the difference is largely because of potential laser strength differences. So as good as I got as moving the laser around all the time in different positions and optimizing the laser strength, I wasn't able to get the same laser strength in all positions. So we get this big spread of laser on minus laser off temperature values. And so we get up to 90 degrees or so temperature difference. But as we go to smaller baffle diameters, effect is effectively reduced. And putting this in RL perspective, this dimensionless parameter of the light restriction, again, we see that there's no baffle, we see this huge range of values up to 90 degrees. But when you add in the smaller and smaller baffles, it reduces the maximum laser on, laser off temperature difference that we observe. So even with some light restriction, we maxed out at about 50 degrees. And as we got down, even for all these 2 millimeter baffles in different configurations at the smallest sizes, we were able to keep it below 20 degrees, which for ion chamber temperature will be enough to keep out these effects that we're worried about. So this light restriction is the primary driver of this ion chamber temperature reduction. So I'm going to just mention this briefly, that this is a bit out of date because I was using 100% temperature change, and in the paper we more accurately described it as 65% or 67% and 90% differences. What this is showing is that the stack baffles just essentially increase the amount of time. So since they're thermally coupled, it make it take 2 to 3 times longer for the temperature change to take place. And what we really wanted was for that time to be lowered instead. So we did not use the stack baffles at all, but they were effective in the ways that we described before. I'm also going to talk really briefly about the source of this laser on, laser off difference. So for organics, I'm showing here. For the organics I'm showing here, we have the open signal and open. In open circle, it's a closed signal and closed circle, and the difference in lines. What you can see is that we see the laser on higher than laser off in both the open and the closed. So we see that in the fast data, and we see it in the slow data. And when we have the baffles on, we see a much smaller difference. So this shows us that if we, another point is that if you don't have a baffle in your system, that this transition point could be an issue. So because the open and closed are sequential, when you would have an issue with this temperature difference, it would happen at this transition point where your open and closed might not have happened at the same temperature because the temperature is changing so quickly. So we have some recommendations on how to avoid that, including taking more than one data point per switch. Okay, so what is the effect of the baffles? We did technically 6 experiments, but we atomized 300 nanometer ammonium nitrate, ammonium sulfate, and glutaric acid in both the baffled and unbaffled scenarios. And we also took ambient data at our lab in Billerica, Massachusetts, near a local highway, the same laser position and intensity. And what we can see is that For this atomized data, we see an improvement in the sulfate from about 8% down to no difference between laser on versus laser off. And that's really great. And we're really happy with this result. For this baffled scenario, you know, this is effectively removing this as an issue. So we see that these unbaffled results are similar to what we expect based on the volatility of these components. And so this reduction of 4 to 8%, 4 to 8% based on the compound is what we see for the atomized case. If we look at the ambient data, I've added in the data from ClearFlow that I showed in the previous figures. This is the summary version. And what we see is that there's not really any difference between the unbaffled and the baffled scenarios, that this effect of the temperature that we see with the atomized is real, and we see this change, but it's dwarfed by these differences that we experience in the ambient based on CE or RIE. So we're going to go back again to this slide one more time and say that this effect of the ion chamber temperature difference is real, and we can improve things by up to 8%. And this would be really important for laboratory characterization of these aerosols. But we can now go on to look at the CE and RIE differences that we see in ambient data and probe those some more to get the answer to these questions. So I think I'm just about out of time. So I'll just mention these conclusions that the baffles are effective in reducing heat from stray light. The light restriction is the primary driver of the reduction in ion chamber temperature difference, but that this effect is only about a 5 to 8% change depending on the compound, and it's dwarfed by other differences that we see in ambient air. And these strategies that we recommend include keeping the laser really well centered, both horizontally and vertically, and sample more than one, we call it run, between each switching, and switch no faster than maybe 5 minutes to make sure that the equilibration has happened. And then I know I'm a little bit out of time, but I just want to mention that, you know, in lots of different ways, people say that science is always building on other science. And for the AMS community, that's very true. And, you know, there's been 20 years of AMS development. All of my co-authors, as I mentioned, have been working on AMSs for a lot longer than I have. So I'd like to acknowledge other people that have helped make this work possible. So for the formal acknowledgements from the paper at the top, Barry did a bunch of work looking at the ray tracing for the laser, and then the other colleagues at Aerodyne with the development and the paper itself. I'd also like to thank all the people who attended AMS users meetings and seen all of Doug Worstop's favorite slides over the years, and really criticized the instrument, developed the instrument, interrogated what could happen in different situations, and interrogated both their results for their scientific work, but also how the instrument works. And you know, I really wouldn't be here today without those contributions. And then, you know, the generations of AMSs that I mentioned before, and then other papers that really contributed hypotheses that we discussed here, and were really essential to this work. So I'd like to thank everyone for listening, and I'll take any questions.
Thanks for the nice talk, Anita. And I think it's time for the Q&A session. And I'm Sang-Hee Han from University of Florida. And yeah, so far I didn't see any question in chat. So if you have any question, please unmute yourself and directly ask to any question to Anita. Is there any question?
Hey, Anita.
Yes.
Hey, this is Subu here.
Hi, Subu.
Nice talk. So I guess towards the end, you showed the comparison of your Billerica measurements with the ambient measurements, and it appeared to that, yeah, exactly. And I'm assuming the green is organic aerosol. Aerodyne colors. And but the baffled is actually a bit higher than the unbaffled, Or did you say that the baffling doesn't seem to make a difference in the ambient aerosol, but so how do you explain that?
So I wouldn't say it's better or worse in the ambient data. So I would say that these are relatively similar. They're slightly different amounts of time. It was about 2 days for each, but there was more data for the baffled than the unbaffled. So we think that this is because that the differences in RIE and the differences in CE that you see from an actual mixture of aerosols are going to lead to those differences in CE and RIE. And so, you know, I think this effect is valid for these non-mixtures, these non-black carbon containing compounds that we atomize. But I think when you have a mixture of any variety, then you're going to get this effect.
Okay. And do you think that mixing state will play a role? I mean, especially if it's a lot of organic aerosol and very little sulfate, as might be typical in the Northeast or the US generally.
Yeah, so it'll definitely have an effect there. So we have started to look into this. So a lot of papers, the Willis paper I mentioned at the end, and Alex Lee's paper I mentioned, did try to parameterize these based on a coating to core ratio. So the issue with that, with those are that it's really hard to determine the CE when you're changing the coating to core ratio. And so those have both suggested this issue of the CAE or the RIE differences. So we think that's the major effect. We are looking to it into a little more, but that'll hopefully be the subject of another paper in the future.
Great, thanks.
So is there any other questions? Actually, I can see one question in chat, and it's about the accuracy of sea salt measurement of AMS.
The what?
Accuracy of sea salt measurement in AMS.
Yeah, so in general, for sea salt measurements, we expect that, so the Middlebrook et al. 2012 paper talked about a composition dependence, but it's also a humidity dependence. So for the, or better described as a solid versus liquid dependence. So particles that are more solid are more likely to bounce. And so if you haven't dried your sea salt, if you haven't put it through a dryer, they're going to stay wet and more liquid and less likely to bounce. And then there's some other considerations depending on the composition of the sea salt, but we do see things like chloride can sometimes vaporize slowly. So there's some ways to look at that to get around that issue. But it depends on the state of the aerosol and of the composition. So I would refer to some of those other papers that have looked at that CE value.
Then, there is one more following question: that will the laser also help the sea salt measurement?
No, so the sea salt wouldn't absorb at 1064 nanometers unless it were, I don't know, somehow black carbon and sea salt at the same time. I guess that could happen. Maybe someone has tried that, but that would be the only case that would be helpful.
Thank you. And is there any other question from?
Hey, I have one more,
Sure.
if there's time. Having worked a lot with the SP2 and having seen people work with the SP-AMS, and there's a lot of time that we spend in laser alignment, trying to get the, and my worry, if I were to, try, I mean, I luckily so far have escaped the AMS, but if I were to use one, adding these baffles and with all the alignments that you described, do you think that just adds more alignment effort than is worth the benefit?
So it does. So it can make it harder. But the good thing, I didn't mention that when I talked about the difference between the three baffles, but the good thing about the cylinder baffle is you can have it in place when you do the alignment before. So on an AMS, when you're aligning the laser, you take the top off, and then you use a jig to align the laser while it's at ambient pressure. And so the benefit of the cylinder baffle versus the other ones is that while you're using that jig to do the primary alignment feature, it's already in place. So it can make it a little more difficult, and it is slightly more difficult. But because you have it in place when you're doing the major alignment step, that it's not like you try to align it and then you put in this new restriction. You do it as part of the alignment. So I understand. We actually tried to do an even smaller baffle and I couldn't get it to align because it was too small. So that is something to consider for sure.
Great, thanks.
So is there any other questions? If not, actually, I have one question. Like I saw a lot of like a plot from the organic and sulfate and things, but I remember that organic is from the alpha-pinene ozonolysis, right?
In the figure near the beginning?
Yeah.
Yeah.
So can it be different if you use different organic?
Absolutely. And this, I guess it's not letting me do this. So this will be slightly different, but this also would potentially have different RIE issues. So you're going to have both CE and RIE issues depending on which you use. So this was used as a surrogate for kind of a mixture of both oxidized and non-oxidized organic, mostly oxidized, but kind of an atmospherically relevant mixture instead of just a single compound here. So it could be slightly different, but this is a rather extreme case. You know, when we're most of your detection is in the 600-degree range. This is a bit extreme, but it's kind of just using it to identify what can happen in this range of ion chamber temperatures.
There is another question in chat. How the SP-AMS is comparable to SP2 when tungsten vaporizer is off?
So, so the SP2 is just measures the scattering and incandescence. So you don't get anything about the chemical composition. So to your point earlier about an alpha-pinene ozonolysis coating on a black carbon particle versus maybe an HOA hydrocarbon coating, you know, from the vehicle exhaust, for a SP2 instruments, you wouldn't be able to tell the difference. You know, that maybe a little bit that they would both produce a scattering signal in addition to the incandescence from the black carbon. But for us, we can look at the mass spectrometry. We can see the mass spectrum of the organic coating as being different between something like that, between different types of coating on the aerosol, instead of just saying, okay, well, there's some coating. The SP2 will tell you that there's some coating, and the SP-AMS will tell you what the coating is.